welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at getting help with the material from Chapter 13, which changed quite a bit with the new version of the test because colligative properties and a number of other things were dropped. So we've got a few less things to look at here. Like always, watch your units. 2, there's a couple of vocab questions, so make sure you're reviewing your vocab because a simple vocab question is a terrible place to throw away points. You need to be familiar with and know what to do with the different types of concentrations we talk about. Understand when you're dealing with solubility in water, how you can use formula as well as other clues to determine which is more or less soluble. And then finally, dealing with molarity and mass percent or parts per million, parts per million conversions. All of those are probably the biggest areas of struggle on the test. First, like always, watch your units. Always know moles, mass, or liters of what, because you've got in a solution solute, solvent, and solution, and you need to be very sure which one you're talking about. Some of our concentration units that we're dropping actually dealt with solvents sometimes, but we're pretty much going to be looking at solute and solution situations. But keep in mind, they could mention something about the solvent, and you need to know what to do with that as well. So always, always, always be careful of your units. And when you look at the types of concentrations that we're dealing with on the test, you've got the 3 I put in red here: parts per hundred, which is percent by mass, parts per million, parts per billion, and then you have the molarity. And I color-coded it differently because molarity is a little bit of a different animal than our other types of situations, which are all related to each other. Notice on the left side, each of these concentrations starts with the same exact thing. The only difference is what we're doing with it. Are we multiplying it by 100, a million, or a billion? And that's why mass percent is the same as pph. But in each case, make sure you're very familiar with the type of unit that you're dealing with and the type of substance that you're dealing with. So sometimes we're going to be in milliliters, but we really need to be in liters for molarity. So always, like normal, be careful with the different types of units that you're seeing in problems. Second one, make sure you know your vocabulary. It seems like such a basic thing, but there are a number of different types of vocabulary in the chapter, and you need to make sure you understand what it's talking about. What does unsaturated mean? What is saturated, supersaturated, as well as our other types of vocabulary that we dealt with. So make sure you review the vocabulary at the end so a simple vocab question does not trip you up. Next, understand the different types of concentrations. There's 2 different fundamental types of concentrations. We've got the ones that are mass situations, so the amounts that we're dealing with are all masses, in this case of solute and of solution. And make sure that you understand that when we're calculating these different types of mass concentrations, we're always dealing with a solute. So when I put mass of A is the solute in the solution. So it's the mass of the solute divided by the total mass of the solution. And then the other type of concentration that we're dealing with in this chapter would be a mole per liter. That's why I put a mass/volume concentration, because remember, mass is related to moles. So fundamentally, we have things that are really just looking at masses, as well as a situation where we're looking at mass and volume. And when we look at our last thing from the test out movie, when we're converting back and forth between red and blue, that's a really important distinction, and that's why we need density for those types of calculations. But make sure you notice what you're dealing with. So if it's our parts per hundred, parts per million, parts per billion, that you're getting the masses of the solute, the mass of the solution. Those are the 2 things you need to know. And be very careful. Do they give you the mass of the solution, or do they give you the mass of the solute and solvent from which you can calculate the solution? That's something that often trips up students with those types of calculations, because it's a fairly simple calculation. Just make sure you're using the right numbers. So make sure you know what's the solute, what's the solvent, and what the solution is, and which of those they gave you. And then for molarity, remember, if they give you a mass, moles is related to that. And if they give you a volume in milliliters, remember, you have to change that into liters. Next situation is solubility questions. So what will it dissolve in? What is more or less soluble in? The most solubility to the least solubility. There's a number of different ways that it can be expressed, but fundamentally it's the same thing. You're trying to determine how one thing compares in solubility to another. The fundamental idea behind this, remember, is like dissolves like. This is a simple rule that we can use that fundamentally means similar polarities are going to be soluble in each other. So polar typically dissolves in polar, nonpolar typically will dissolve in a nonpolar substance. And what this really deals with is when we look at our ideas from the chapter, this is the three energies based upon intermolecular forces. Energy 1, breaking apart the solute, energy 2, breaking apart the solvent, and then energy 3, the bonds that form between our solute and solvent. Remember, the first two are always going to be endothermic. They need energy. The third one is always going to give us back energy. And the reason that polar dissolves in polar and nonpolar dissolves in nonpolar as a general statement works is because when we have like solubilities, 1 and 2 tend to be comparable to 3. And as long as 1 and 2 are similar to 3 in energy, then it's going to be soluble. And remember, even though it's endothermic overall, the entropy increase that we discussed in the chapter can make up that difference and it can still be soluble. But when 1 and 2 are not comparable to 3, 3 is just not big enough to overcome uh, or for entropy to overcome, it won't be soluble. And typically you'd see that in something like an ionic compound dissolves in water, which typically involves a large number 3 energy because ion dipole is a strong type of attraction, which means it's going to release a bunch of energy. But if the ions that we're breaking apart are held together by too high of a lattice energy, that's going to affect if it's soluble or not. And it's also going to affect its solubility. The higher those lattice energies are, the trickier it is to dissolve. So those are going to cause your solubilities to go down. But fundamentally, one of the things you're looking at here is really, is it a polar or is it a nonpolar thing? Now, as far as recognizing nonpolar, and this is a really important one, remember the types of things that are dead giveaways you've got nonpolar is when you've got your noble gases. Those are all nonpolar substances. Or typically, honestly, if it tells you in the situation that gas A is a gas, then that's kind of a dead giveaway. If it's a gas at room temperature, then it's likely a nonpolar thing. But remember, our noble gases are one of the things we talk about. Our diatomic molecules, those are also things that are predominantly gases, but diatomic molecules have perfect symmetry, and that means they're going to be nonpolar in nature. So noble gases, diatomic molecules, and then are other types of molecules that also have perfect symmetry. Two to watch out for here would be tetrahedral things. So CCl4, CBr4, CH4, those type of things. Those are all tetrahedral, dead giveaway that we're going to be looking at a perfect symmetry the vast majority of the time. And then finally, carbon dioxide. You know that's a gas at room temperature. That's because it's a hidden linear, and that has perfect symmetry as well. So even though the bonds are polar covalent, it's a non-polar molecule. And the last one to watch out for would be hydrocarbons. Compounds containing carbon and hydrogen. The bond types between two carbons and a carbon and hydrogen are all non-polar covalent. So they're always going to give you a non-polar molecule. So with nonpolar things, noble gases, your diatomic molecules, tetrahedrals and CO2, and then finally your hydrocarbons. Those are the types of things that are typically nonpolar. If you have a molecule and you're just not sure, you can always draw it to see if it's got perfect symmetry. Other ones that might pop up from time to time that would be perfect symmetry, beryllium compounds. Remember, beryllium's in a deficit octet that forms a linear with perfect symmetry, and then boron compounds. It's a trigonal planar situation that would also have perfect symmetry. You're not going to run into those as often, but those are a couple of other situations that you might run into. So if it ends up trigonal planar like an SO3 because of resonance, then that would also be nonpolar. But the vast majority of the time, it's going to be noble gases, diatomic molecules, some simple perfect symmetry situations, or a hydrocarbon. Everything else is typically going to be polar if it doesn't fit into one of those categories. So your non-symmetrical molecules, binary molecules like HCl that aren't the same. So we're not talking about diatomic molecules, two non-similar elements making a molecule. And then the biggest thing, watch out for hydrogen bonding. Hydrogen bonding is like almost the first thing I look for when you look at a molecule. Anything that is strong enough, remember H stuck to an NO or F as a molecule, is going to have hydrogen bonding. So great examples would be water, ammonia, which is NH3. Alcohols have the OH functional group on them, and that's always going to give you hydrogen bonding. And then finally, the carboxyl group. If you recall Cu from earlier in the year, C double bond O OH, that also is something that is going to end up having hydrogen bonding. So those would always be your polar type situations. Now, once you know whether it's all nonpolar or polar and nonpolar, remember typically polar things are going to be soluble in polar things like water. So once you've got polar versus the rest being nonpolar, go with the polar. So if one thing had a hydrogen bonding and the rest were all nonpolar, you know it's going to be hydrogen bonding. Where it's sometimes trickier for students is if they're all nonpolar, what do you do? Or if they're all polar, but you look at it and you realize, well, their polar parts are all the same. How do you handle those two situations? Well, first, when it's all nonpolar, remember nonpolar LIMPEC, larger, more polarizable electron cloud, controls your intermolecular forces. And the stronger the intermolecular force of a nonpolar thing, the higher its solubility is going to be. I'm not saying we would call them soluble. Nonpolar things are classified as insoluble. But remember, insoluble doesn't mean it doesn't dissolve. It means it only dissolves to a small amount, not high enough for us to classify it as soluble. So it still will dissolve. And I guarantee you, the stronger the intermolecular force, the bigger the LIMPEC, the more soluble in water it's going to be. So if they're all nonpolar, think of LIMPEC. And then if they all are polar molecules, but you notice they all have the exact same polar part. So let's say we had a compound that had carbon, carbon, and then a Cl, or a carbon, a carbon, a carbon, and a Cl. Fundamentally, both of those have that same polar part, that chlorine stuck to the carbon, because remember what I'm not drawing in here are all the hydrogens. That's going to make that part polar. Well, these two have the exact same polar part. So what it really is going to mean is zero in on the nonpolar part. So treat something that has the exact same polar components as if it's a nonpolar thing. And then think about LIMPEC. The 3 carbons are going to give you a larger, more polarizable cloud. So I would expect that the second compound, this one, would be the one that's going to be more soluble in water. Now, the last thing to prepare for in the test is probably the more challenging thing mathematically to handle, and that's converting back and forth between molarities and our concentrations that dealt with mass, ppH, ppm, and ppb. Now, one of the most important things about this is to first take stock of what it's telling you and then write that stuff out. And remember, we want to separate and find out the mass of the solutes, the mass of the solvents, and the mass of the solutions. If we know those 3 things, we can go lots of different places. And you need to understand when they're telling you something that actually gives us information. So one of the first things you should remember is try and isolate what is the mass of my solute, what is the mass of my solvent, and what is the mass of my solution. And remember, those are related to each other through this equation. The second thing that's going to be key to this type of problem is the density equation. And it may help to actually write this down so that when you're looking at the information you're given, you can see what you already have. So density of the solution is equal to the mass of the solution over the volume of the solution. And in every single case, what you're really doing is you're going to know 2 of these things. If they tell me the density and I can establish the volume of my solution, then I can solve for the mass of my solution. And if I know the mass of the solute and the mass of the solvent, I can get the mass of the mass of the solution and the mass of the solute. I can get the mass of the solvent if I needed it. Or if they give me the density of the solution and I know the mass of the solution, I can determine the volume of the solution. So in every single case, you will have a situation where you know 2 of these. And when you take stock of what you know, writing this equation can help tell you what you don't know. And then remember to write your concentrations as the fractions they represent. And this is really tied back to number 1 and number 2. So if it says 12%, remember that means 12 grams of solute per 100 grams of solution. So technically, if I needed it, I would know I have 88 grams of solvent. Now, we're assuming that we have 100 grams of solution and that we have 12 grams of solute. So remember, in this case, I'm locking myself into those are my quantities of solute, solution, and finally the solvent that I could figure out. Now, if I knew the density, by the equation number 2, if I knew I had 100 grams of solution, I know the mass of my solution in the density equation. And if I know the density, then I could use that to calculate the volume of the solution. If I change that into liters, if I'm in milliliters, then I would know how to calculate molarity, because molarity is moles per liter. I could then plug that into the molarity equation, establish my moles of solute. I just talked about how to get the liters of solution, plug them in, and you got your molarity. Now, the other thing is when you're dealing with molarity at the beginning. If it tells you you're a 12 molar solution, remember that means 12 moles of solute for every 1 liter of solution. So that's locking me into that amount of solute. I can use molar mass to get that to grams, and I know, though, the mass of my solute. And it's also locking me into 1 liter of solution, which if I knew the density of the solution, once again, If I know this and I know that, I can solve for this. And that would give me my mass of my solution, which I would need for my percents. So I can get the mass of the solute from the moles of solute, and I can get the mass of my solution from the density equation, the fact that I have 1 liter or 1,000 milliliters. And as always, pay attention to units, because if you're in milliliters and need to be in liters, you got to do that change, and vice versa. So be careful of the units you're in. But that's really all there is to these types of conversions. Remember, there's 3 fundamental things that you need to be aware of: the relationship between the mass of the solute, solvent, and solution, and the fact that you really need to establish those 3 quantities; the density equation, which you're going to use in every single case to help bridge the two; and then remember, whether they give you the percent by mass, the pph, the ppm, the ppb, or they give you molarity, that establishes a relationship between solute and solution that you need to know. So write out that fraction, write out that equation, and it might also help you if you actually write in the words solute and solution so you can keep track of those things. Otherwise, that's most of what you need to do that's trickier for students to help prepare for the test. So good luck preparing.